Lucia Specia is a professor of natural language processing at Imperial College London. Her research focuses on various aspects of data-driven approaches to language processing, with a particular interest in multimodal and multilingual context models, and in the intersection between language and vision. Her work can be applied to various tasks such as machine translation, image captioning, quality estimation, and text adaptation. Let's welcome Lucia.
Thanks, Diego, for the introduction, and big thanks to all of the organizers for doing this and for having me here. I'm originally from Brazil, like many of you, and I'm very happy to be part of such an event. Right, so what I want to talk to you about today, is sort of approaches that try and make NLP a bit more of a holistic approach to language rather than what we have in most applications where you're taking text and doing something with it. And by holistic, I mean where you're taking other modalities in addition to text. So why do we want to do that? Well, we all know that language is very hard, whichever the language we're talking about. If we're given a sentence like this, even us as humans, without any further context, may have trouble deciding whether the meaning intended is the first or the second. And I could give you many such examples where we have many language ambiguities on different levels, and even for us as humans, it's hard to make sense of that without any additional context. And in a lot of the application, the presentation today, the additional context will be visual, but this extends to other types of modalities as well. And the way we humans manage to deal with it is by using this more holistic way of processing a language. Sometimes it's by our background knowledge, but a lot of the times it's by using other modalities. So there is an area of machine learning, or a sub-area of machine learning called multimodal machine learning. And what this area tries to do is exactly that, is to build models that will leverage different types of modality, which basically means we have richer context models. It's all about context. And the modalities can be various, text and vision, be it static vision, or images, or videos, or hearing. And of course, you could try and think of bringing this forward and having like tactics and other modalities, but in practice, it's mostly text, vision, and hearing. And in the case of language, which this is what this talk is about, what it means is that we're grounding language in another modality. So to try and put this in very abstract ways, on like how do you do this? How do you do multimodal machine learning? The good news is that deep learning or neural models make this a lot easier than in the past. And this is a very abstract representation where we would have as input different modalities, say text or acoustics and or video or images, and we have as output a certain type of output. In this case, mostly language. It could be a language that is different from the input language, and in this case, I'm talking about translation. It could be a shorter version of the input language. It could be a transcription of the acoustics, and the input could be a combination of any of 2 or 3 in this case, at least 2, otherwise it's not multimodal. And the output in our case is mostly text or a class, but you could extend this and think that the output could also be image. It could be either generating or selecting images, or generating speech, or generating a video, or selecting a video, or retrieving a video, and so on. But the important thing is the middle bit there. So you could think of creating models that would use whichever neural network to encode the modality. So say you'd have an LSTM or a transformer to encode the text, then you have a CNN to encode the video or the image, you have whichever model to encode the acoustics, and you end up with these independent representations, and then you need to put them together somehow. So the simplest way of putting this together would be, say you just have, you have something that concatenates different representations here. So the middle bit here is simply a concatenation of different embeddings. More elaborate things could be, this is somehow learned jointly. So you could have, for example, multitask learning, where you're using the different modalities and different tasks. Say, you're using text to learn translation, you're using images and text to learn captioning, but you're training this jointly, such that you have shared representations here. And there could be many variants of shared representations here, depending on how much you want to share. But this is sort of the general idea. And one important distinction that we tend to make is whether this middle bit is a simple case of fusion, which is, for example, the concatenation that I mentioned, where it could be done actually even before you learn the embeds, but generally is done afterwards, so late fusion. And in that case, say you extract your language embeddings and your visual embeddings, and then you're simply putting them together somehow. And the other type of model is a mapping model, where you learn a function to map between the two modalities. And generally, we're talking about mapping elements from one modality into elements of the other modality, say objects in an image to words in a text. And this is a much more interesting, conceptually, much more interesting model. It's also much harder to learn. And most of my presentation will be about somewhere in between these two, which would be this kind of model with attention, which somehow learns this mapping. So this is the overview. So I'm going to basically give you some examples of applications. There are many. And then most of the talk will be about one of these applications, which is multimodal machine translation, which is a reasonably new or recent application. And I'll focus on trying to understand whether we need a second modality there. In this case, either static images or videos. When does it help? When does it not help? And why? And I'll show you a couple of probing experiments for that. So in terms of applications, an important distinction that I like to make is applications that are primarily language applications, where we add another modality as a way of helping the language application. So this is just some examples. Coreference resolution, sentiment analysis, parsing, and so on. Translation is one of them. And applications that are inherently multimodal, where you do need the two modalities, otherwise doesn't constitute the application. For example, visual question answering, where you were asked a question in natural language about an image, and you have to answer that question. So in principle, you need the image, even though there are some studies showing that you don't always need it. So let me just go through a couple of applications very quickly before I get to translation. So the first one is Coreference Resolution, which, like I said, is an example of application which is a language application where we can use images to support this application. So this is somewhat a couple of years old now. And this was doing it using videos and the subtitles of the video. So the task is to resolve pronouns and references like, in this case, he or engineer, by finding out which antecedent in the text that refers to. And they're doing that by using the video as well, and by also using scripts of the, in this case, a TV series, to identify what characters are in this TV series. So the way they do it is, it's a model that is doing a bunch of things. The first one is detecting people in the video, so finding basically faces in the video, and then trying to find the names of the characters that can be assigned to those faces. And then at the same time, well, not at the same time, after that there is a step of trying to align this to the actual subtitles, and then finally to align the names to the identified references in the subtitle. So this is sort of the final outcome, where you have things like he, which has a specific antecedent here, and same as foreigner, and so on. So in this case, the visual information helps identify these antecedents. Another example of application is sentiment analysis or classification. And this is somewhat, again, a bit old, but it's sort of the simplest thing you can do. You'd have your text, in this case is a movie review, and then you'd have either some pictures or or the actual, like a snippet of the video. But let's just say you have some pictures. So you're embedding your text using, in this case, an LSTM. And then you have two different CNNs here, one doing object detection, the other doing scene detection, so identifying if it's indoors, outdoors, or whatever type of scene. And then you end up with three representations which are somehow fused, and then you have a softmax to decide what is the sentiment at the end. So very simple architecture. An example of an application which is already like a multimodal application is the one I mentioned, a visual question answering. So we've seen this before. So you have a question about an image, and you have to answer that. So this is, again, probably the simplest thing you can do. There are more advanced ways of dealing with this problem. But just for the sake of simplicity, what you'd have is somehow you're encoding your image. In this case, you have probably convolutional feature maps of the image here. And then you're encoding your question using an LSTM or CNN. And then you have attention over from the words to the regions of the image. And then at the end, you have, again, a softmax, which is predicting possible answers given your vocabulary. And then finally, visual dialogue, which is an extension of visual question answering, where in addition to the question, you have a bit of a history. So the question here says, what color is it? And unless you resolve it based on the textual history here, and potentially the image as well, you can't really answer that question. So you need to encode this history as well as the question and the image to be able to answer this question. And the architectures, again, can be similar to visual question answering, but there are more advanced architectures there. Okay, let's focus now a bit on the application that I've been working on for the last couple of years, which is multimodal machine translation. And this is just a general representation of the possible variants that one can have there, where the modalities are text, speech, and video or image. So in principle, there could be any combinations there. And we distinguish unimodal, which would be, in this case, text to text or speech to speech directly, so an end-to-end model, from all of the blue variants. And the blue variants would be the traditional spoken language translation, where the input would be the audio or the speech, potentially also with the video if it's a multimodal approach, and the output is text. Then we have what most people have worked with so far, which is text plus image, so image-guided translation. And finally, you can have video and text, so video-guided translation. And of course, you could have video plus audio plus static images. You could think of any different combinations there. It's all data-dependent, so it depends what you have as a data set to train this. So what I will cover in most of the presentation is actually text and image. There's a couple of slides on video as well. So the additional modality is static images. So why do you think this can be helpful? So let's just start with an example. So this would be a standard translation task where you're given an input text and you need to produce an output text in a different language. Here we notice that this text is actually a description of an image, so it's an image caption, if you like. So this is how we started building these models in this field. So we started with this assumption that the text is semantically equivalent to the image to some extent at least, which makes it easier. But of course, this extends to text that is not entirely, say, aligned to the visual content. So in this case, something happened? Okay. In this case, we have one ambiguity here, which is the word hat. When translating it into German, you need to make a decision between a summer hat or a winter hat. In English, we don't have to do that. And again, if we don't have anything else here, the translator, be it a human or a model, will have to make a choice. And in this case, they choose the winter hat word. If we see an image and we can detect that there are things like, I don't know, beach scene or sunshine or even the color blue there, this might be an indication that this is actually a summer hat. Another classical example is that of gender disambiguation. So these are actually real examples from our data set, which were originally translated by a human without the image and then fixed by that human looking at the image. So the word player in English it could be male player or female player. And if we see the word baseball, our normal biases or our language biases would probably lead us to think that this is a male or a masculine form of the word. And that's how it was translated by our translator into French. However, if we see the picture that corresponds to this description in the data set, and we can detect that there are two women there, then we know that the translation should be different. It should be the female version. Right, so how do we go about encoding the two modalities there? So for text, I don't think I need to say much. We've already seen how we encode text in the previous presentations. For images, you've seen maybe a bit of that. We basically extract these features beforehand. We use a pre-trained CNN, which is normally trained to classify objects on ImageNet, and we can use different layers or different representations learned by this network. And this is an old network. We use more recent ones like ResNet, whatever number of layers. But basically, yeah, you could take the different convolutional feature maps that you have in this network, or you could take a more like sort of a summary version, so say the last fully connected layer or the last pooled layer of your network, or you could even take the output of the network, which is this distribution over, in this case, 1,000 categories of objects. Another thing that we did in our group is to try and learn from more abstract representations of the image, where we actually running more, running other types of CNN networks to extract information first, and then using these abstractions as input to the text network. So one of the things we do is object detection, and then say we just run a state-of-the-art tool. We find that there are cars, there's a bicycle, truck, and so on. And we represent this by taking some pre-trained word embedding of these categories. So we're going back to text, but just as a way of having a continuous representation of these categories rather than just a discrete set of symbols there. We do the same with actions when you're dealing with videos. So we run an action detector, and then we represent, say, the top, 10 categories of actions by using the word embeddings. And this is the type of representation that we give to the text network. And this can be done with colors, so you have color detectors, scene detectors, and we've tried all of those things. Right, so how do we put the two sources of information together? So in the context of RNNs, which is where we started, this is fairly straightforward in many ways. So the simplest thing you can do is to take one single vector from your image network, say the last pool layer, and then use this vector to do different things in your, so this is just, this is a standard encoder-decoder RNN-based network for translation. One of the things we can do here is to just use this or some projected version of this vector as a way of initializing your encoder or initializing your decoder, or you can do some element-wise multiplication at encoding time or decoding time. And this works well to some extent. And it starts to bias the text network with this information. We can do a little bit better by using attention, visual attention in addition to the text attention. We already had a text attention there. And the simplest thing you can do here is to use, again, the convolutional feature maps here instead of a single pooled layer. And then you have visual attention at decoding time. So every time you're generating a word, you learn where to attend to in the image. And you combine the visual and textual attention in different ways. You could, again, simply concatenate them. You could have another layer of attention on top, so hierarchical attention. You could do different things here and decide how much of the parameters you want to share. And in the sort of more recent era, transformer-based, the most obvious thing to try is to add another layer of attention, which is a cross attention, but it's a visual cross attention. In this case, at the decoder block, there's some variants of that, but this is probably the simplest thing you can do. So you still have your standard, this is just a standard encoder block, but then you have your standard decoder block where you have your self-attention, your text cross-attention, but also visual cross-attention. So you're attending to the image when generating words. And the representations here are similar or the same as the ones I mentioned before. You could have, without attention, you could just have your summary vector here, which in this case we're just doing some element-wise multiplication at encoding here, at the output of the encoder. But you could also have attention over these embeddings, word embeddings of the categories of actions in this case, or you could have attention over convolutional feature maps. So let me just try and give you a flavor for how this works in a data set that we've been using for this task. So this data set is called Multi30K, which is an extension of Flickr 30K, where we already had images and some annotations, so bounding boxes, which I'm not going to use in this presentation, but and descriptions in English. So what we did was to collect translations in 3 different languages. And this is very small, only 30,000 pairs of descriptions and images. But the language is very simple, as you can see from these examples. Very short sentences, on average 12 words. Very simple grammar, very repetitive sentences. So we are somehow able to learn models with this very small data set. So this table summarizes the results of the latest shared task, which we ran last year. This is English-French. We had the 3 language pairs there. And all I want to highlight here is we use Meteor, which is this metric that compares the system output to a human translation and some sort of like string similarity way. So the higher the better. And what I want to show is that so there was a top system here, which was actually multimodal, but it also used a lot of external parallel data, so it's not clear whether they're doing well because of multimodality or not. So, but if you look at contrastive systems that are actually the same, except for the use of images or not the use of image. So this case, for example, the Kuni system has a version that is text only and a version that is multimodal. We see that the text only is actually doing better than the multimodal one, according to this automatic evaluation metric. And this is disappointing. And this is what we've been observing with a number of experiments, at least on this data set. And there are other contrastive systems that are the same. So the text only is better than the multimodal version. But however, when you look at Czech, which is one of the other languages in this data set, we notice that the results are different. And this is the same contrastive model. This is the multimodal version, and this is the text-only version. And the difference is quite large. So this let us think that maybe the problem is not that these models don't work with visual information, but rather that for certain language pairs, it's too easy to translate based on the text only. So to find out whether this is the case, we designed a bunch of probing experiments, and I'm just going to talk about 2 of them here. So the hypothesis, yeah, language is too easy, there's no ambiguities, there's no noise, there's no out of vocabulary, so it's not challenging and images are not needed. So the models just learn to ignore the image, even though in some cases we know there are ambiguities, but there are very few. So the question is this always the case? So briefly going through these probing experiments, what we do is we try and make language more difficult by systematically hiding some words. So similar to the BERT idea of masking, but we are not trying to learn we're trying to learn what the translation of these words are. So we have placeholders for different things. One of them is color-related words. So we traditionally in vision, we think that the models are good at least understanding colors. Entities, which are things that we know are mentioned in the text because we have the bounding box annotation, and I'll show an example in a minute, and just systematically deleting words. So I'm going to show that in context with examples. So color masking basically means whichever color word we replace it by a placeholder, it's always the same placeholder for every word that we replace. And we only do that, of course, in the source language at training and test time. And the target language remains the same. So in a way, we're trying to make the models guess what these words are by looking at the image, because they can't guess. Sometimes maybe they can guess that from the text because it's obvious, but not always. So how does this perform? So these are different models without any color and any sort of masking. NMT is a text-only model. And the 3 bottom ones are multimodal models, different flavors of RNN-based multimodal models. And as you can see, there's pretty much no difference here without any masking. When you do the masking, the performance drops, as you would expect, a little bit, because there's only 3% of the words that are masked. But they drop less with the multimodal models than they do with the text-only models. So this is a good sign. When we look at the more interesting case where we mask more words, so these are the entity words. So these are things that we had bounding box annotations and links between the image and the text in the data set. So we know that man and lady appear in the image. So we mask this too. Then the results are very different. So here we have our text-only model. So it drops about 20% compared to the version without the masking. We're masking 26% of the words here. And the 3 bars here correspond to 3 different multimodal models. And as you can see, the multimodal models are able to recover from this drop performance quite a lot, more than 4 Meteor points. And if you look at one example or 2, just to see what's happening. So this was what we masked. A drinks outside on the reference should say dog, water, grass. And with the text-only model, we get man drinks wine on the sidewalk. Maybe men in this data set drink more wine than water. With the multimodal model, we get pretty much the correct translation there. And one interesting example in this data set, which actually shows what's happening, is an example where there was a typo this is we didn't do anything about it. It was there in the data set, so it should have said sun, but it says song. And because these are entities, we end up masking these two. And the correct translation should be to French, this is mother and this is child. When we look at the two types of attention, so this is the first version without any masking. And we can see that the text attention is pretty strong. It's doing a pretty good job there. But the visual attention is a bit lost. So first it's pretty much always attending to the head of the mother there and nowhere else, and it doesn't vary much. When we do the masking, however, which we think it's forcing the model to look at the image more often or more effectively, this is exactly what happens. The text attention is not as strong, so the links between the masked words and the target words are less clear. And we see that visual attention is actually working. When we are translating the word mother, when we're generating the word mother, it's actually really attending to the mother. When you're generating the translation for what would be son, which is masked, is actually attending to the child. And it's generating, sorry, it's this one. It's generating the right translation, which is enfant in French. And just for sake of completeness, this is the last experiment where we mask everything progressively. And you see that in the last case here, it becomes much closer to image captioning, except that we have an information about the length of the sentence, the expected sentence. And what happens is that this is the delta in Meteor, so the higher the better, between the text-only model and the multimodal models, the 3 multimodal models. And this is the amount of words that were kept. So in the extreme case, so we have no words in the source sentence and basically guessing the translations with the image only. The gap is, of course, the largest. And then as expected, as we add more words to the source, the gap is smaller. So in a nutshell, this is basically showing what we hypothesized, that the language is too simple, but the moment we start making it more complicated, the image is used. So I'm going to skip over a couple of examples, and I just want to show you one final set of experiment, which is quite interesting, where we're dealing with videos instead of static images. And in this case, instead of simulating the noise, we kind of get noise naturally by treating this as a spoken language translation, as a pipeline spoken language translation task. So first we do ASR, or speech recognition, which is noisy. In our case, we have a very noisy ASR with 19% word error rate. And then we take that text and we build a model to translate it. In this data set of videos, it's into Portuguese, and we expect the videos will be able to help. And we're translating here subtitles of the video, which are not descriptions. They're just standard subtitles, so basically a transcript of what the person is saying. And they're talking about different types of things, these are instructional videos, how to do things, but the image is not always aligned to the text. And this is just a summary of the results, different models, but this is a text-only model, and these are multimodal models, and basically with our best models, we're able to improve 1 point in Meteor, which is actually significant according to this metric. Right, so just to summarize, so in general, not only for translation, but in a number of applications, it's been observed that multimodal context models provide useful information for language tasks, and that the current representations or features that we extract from CNNs and the models that we have to put them together with text can already leverage this information, but only if textual information is not enough. And here I'm talking about a class of applications where you also have text as input. And this can be because the text is ambiguous or too short or too noisy, or you have non-standard input out of vocabulary and so on. And moving forward, I think there's a number of extensions, some of which we've been working on, like translating video descriptions or subtitles, simultaneous translation where you have to do on the fly, you have to recognize what has been said and already translate it before the person finished saying it. More modalities, so you could have combinations of more than 2. There's a lot of work on pre-trained multimodal representation, so basically extensions of BERT, where you're also learning those representations using images and better evaluation metrics and so on. So thank you.